Hello everyone, welcome back. Today we're going to be continuing with grade 12 Matric questions. We are on Physics Unit 5, Steady Electric Currents and Circuit Properties. So let's move on to the question. So question number 23 states that, which of the following statements is correct? Choice A, a galvanometer can be converted to an ammeter of different scale by connecting a variety of low-valued shunt resistance in parallel. Choice B, galvanometer can be converted to a voltmeter by a different scale by connecting low-valued resistance in parallel. Choice C, low-valued internal resistance increases accuracy of voltmeter. Or choice D, high-valued internal resistance increases the accuracy of an ammeter. So this question has to do with the different types of measuring instruments in electric circuits. The main ones that we have to know are voltmeters. Voltmeters, represented like this, are used to measure voltage. We also have ammeters. Ammeters are represented like this, and they are used to measure current. Now, it's not enough just to know what these instruments measure. You also have to know how to position them in the circuit in order to measure what you want. So let's shift the board a bit like this. So if you wanted to measure the voltage across some resistor, for a voltmeter, you must place this resistor in parallel with the voltmeter like so. When you place it in parallel, the voltmeter will be able to measure the voltage across this resistor. Alternatively, for an ammeter, if you want to measure the current, you have to place the resistor in series with the ammeter. The simple reason behind these positionings has to do with the fact that voltage is equal in two parallel lines. So if you see the voltage drop from this area, point A to point B, it is equal. So the voltage drop across a resistor will be equal to the voltage drop across the voltmeter. In the case of current, the current flowing from point A to point B is also equal. So the current flowing through this resistor here is the exact same current flowing through the ammeter here. So this question talks about a galvanometer. So a galvanometer can be used as either a voltmeter or an ammeter, depending on how it is positioned in a circuit. To use a galvanometer to measure current, or to use it as a ammeter, here is how it's done. Let's scoot this down a bit so we can see this clearly. Galvanometer is denoted like this. You have this block, and you have a circle, and you represent this with a G. So, when a galvanometer is desired to be used as an ammeter to measure current, you have to place a low-valued shunt resistance in parallel with the galvanometer. Once you place it like so, then this galvanometer can be used to measure the current flowing through the electric circuit. Now, the reason for this shunt resistance, this is called a shunt, or it is denoted by low resistance. Now, the reason why you have low resistance here is that a galvanometer can only measure a small amount of current. In fact, the range of current that a galvanometer can measure is from 0 to 5 milliamps. So whenever you use a galvanometer, you only want a very small amount of current to flow through it. Now, the current entering into this galvanometer first can be considered I1, and then you have some amount of current flowing in this direction, I2, and some flowing through this direction, I3. When you create this low shunt resistance, most of the current will flow towards the resistance. In a sense, I2 will be much greater than I3. So by using this small resistance placed in parallel with the galvanometer, you can use the galvanometer as an ammeter. Alternatively, if you want to measure voltage, again, we can denote the galvanometer like so. We have our galvanometer denoted like so. You place a high resistance resistor in series with the galvanometer. And then, in order to use this as a voltmeter, you can place your resistor in parallel with your galvanometer. Now, the reason behind this is quite similar as the above. You have your initial current, I1, flowing in this direction, and then you have I2 flowing in this direction and I3 flowing in this direction. Again, you want most of the current to flow through I3. You want very little current to flow through the galvanometer. So I2 in this case should be much less than I3. In order to ensure that, you use a resistor with a high resistance. Due to this high resistance, current will not flow through the galvanometer, but rather will flow through the resistor. So again, in order to create an ammeter with a galvanometer, you place a low resistance in parallel. In order to create a voltmeter, you place a high resistance in series with the galvanometer. And in this way, a galvanometer can be used as both a voltmeter and an ammeter. If we look at the choices, we see that that will be choice A. A galvanometer can be converted into an ammeter by using a low value shunt resistance in parallel. If we look at choice C and D, with logic, we can actually remove these choices from the question, because choice C and choice D are opposite, meaning that either both of them have to be right or both of them have to be wrong. Since this is a multiple choice question, they can't both be correct. So our only conclusion is that both of them are wrong. That is one way to answer some questions, some multiple choice questions, by using logic without even understanding the actual concept of the question itself. But to actually cover the concept of the question itself, let's go back to this setup right here. Choice C says that the low-valued internal resistance increases the accuracy of voltmeter. Well, in this case, let's see. If the voltmeter has low resistance, what will happen to the current? Well, a lot of the current will flow through this direction. We don't want current to flow through the voltmeter. We want current to, in fact, flow through the resistor. So that can't be it. You actually need a high resistance when you're talking about a voltmeter, because you don't want current to flow through the voltmeter. You want it to flow to the resistor instead. Looking at choice D, it says that a high valued internal resistance increases the accuracy of an ammeter. Well, let's see. If you have a high resistance of your ammeter, what will happen is the current flowing through the ammeter will decrease, and in turn, the current flowing through the resistor will increase. You don't want to affect the current flowing through the resistor. So in fact, in case of an ammeter, you need a very low resistance. A very low resistance will allow the current to freely flow through the resistor and the ammeter as well. So that will cancel out choices C and D, leaving choice A as our best answer. And that's it. Now, moving on to question number 24. In the circuit shown below, each resistor has a value of 3 ohms. What is the value of the current through R4? So I'm just going to bring out the circuit right here. So this is the circuit in the question, and it's asking us to find the current through R4. In order to analyze this circuit, we have to use Kirchhoff's laws. So we have 2 laws of Kirchhoff. We have Kirchhoff's voltage law, and we have Kirchhoff's current law. So Kirchhoff's voltage law states that if you add all of the voltages within a loop, they will add up to 0. Kirchhoff's current law states that the currents entering a certain node is equal to the currents exiting a certain node. So I'll use this example to explain both of these laws. When we look at Kirchhoff's voltage law, whenever you have a circuit set up like this, you create 2 loops. This case will have loop 1, and in this case we'll have loop 2. So by adding the voltages in each respective loops, they will add up to 0. Kirchhoff's current law states that if we analyze the current going through this circuit, let's consider this node right here. Let's consider this current I1, and following this loop, let's consider a current I2 like so. Let's say we have a third current going in this direction, I3. And so if you consider this node right here, we see that I2 and I3 are entering the node, and I1 is exiting the node. So you say that the currents entering the node, I2 plus I3, is equal to the current exiting the node, equal to I1. So let's keep this formula in mind. We'll use it later. Now let us use KVL in order to analyze the voltages in loop 1. So let's scroll this down a bit, and let's start with loop 1. So in loop 1, we have different voltages. We have a voltage drop across this resistance. Let's call it V1. We have a voltage drop across here, V2. Voltage drop across here, V3. One across here, V4. And one across here, V5. So we're on loop 1 currently. So Kirchhoff's voltage law states that V1 plus V2 plus V3 plus V4 plus V5 is equal to 0. One thing that we have to consider is that when calculating the voltage drop across the resistance, voltage is equal to current times resistance. This is a very basic Ohm's law formula. Another thing to consider is that when you're considering the voltage drop across a cell like so, this end is the positive terminal and this end is the negative terminal. So you have to consider the direction of the current in order to write down the voltage. That will be clear once we do this example. So we see that V1 is equal to the current flowing through R1, which is I1, times R1, that is V1. Plus, when we look at V2, the trick to writing the voltage as either positive or negative is consider the direction of the current flowing through the cell. The current is flowing in this direction. Take the sign of the far terminal. In this case, the farther terminal is the negative terminal. So we take negative 6 volts instead of positive 6 volts. You'll get the hang with this more questions you do. Moving on to V3. V3 again is the voltage drop across R2. We still have the same current, I1, multiplied by R2. Now in V4, so when considering the current flowing through R4, you can't simply consider I1. A trick you use is, if you're on loop 1, you consider I1, but you have to subtract it from I2 in order to calculate the current flowing through R4. This makes sense if you consider Kirchhoff's current law that states that I2 plus I3 is equal to I1, and this would mean that I3 is equal to I1 minus I2. And we see that here it's actually I3 flowing through R4, and also here we see that I3 is I1 minus I2, so it all works out in the end. Lastly, we have V5, and we see that V5 is this cell of 3 volts. Again, if the current is flowing in this direction, you take the far terminal when you consider the cell. The far terminal is positive, so we take positive 3 volts. All of this is equal to 0. I know it's a lot to process, using KVL, but once you practice it more and more, you get the hang of it. Let's simplify this formula by looking back at the question. The question states that all the resistors have a value of 3 ohms, so we can replace all of the R's with 3. So this will be written as 3I1 minus 6 volts plus 3I1. Let's distribute this R4 for both I1 and I2. So we have, again, plus 3I1 minus 3I2 plus 3 volts is equal to 0. Now let's consider that we have I1 here, and I1 here. Let's also consider that we have minus 6 volts here and plus 3 volts here, and let's put these together. So we have 3I1, 3I1, 3I1. That will be 9I1. We have this minus 3I2, and minus 6 volts plus 3 volts is minus 3 volts, but let's take it to the other side of the equation and make it positive 3. So keep this in mind. This is our first equation. Let's call this equation number 1. Now let's move on to loop 2. So to make things a bit clearer, let us clear this out here, here, here. Let's clear these two out as well. And let's consider the voltages across V2, across the second loops. So let's consider this as V1, this as V2, this as V3, this as V4, and this as V5. So again, the same formula still applies. When we look at loop 2, we see that the sum of each voltage, V1 plus V2 plus V3 plus V4 plus V5, will all equal to 0. So let us calculate first the voltage drop through V1. Current I2, don't be confused, this current I2 is the same current flowing through this whole half of the circuit. So all this is I2. So the current flowing through R3 is still I2. We say that V1 is I2 times R3. Now we look at this voltage 2, or this 9 volt here. Again, if the current is flowing in this direction, take the far terminal. That is positive. This terminal right here is positive. So we say positive 9 volts. Next, we see V3, which is the voltage across R5, and this again is equal to I2 times R5. Then we have the 3 volts. In this case, our current is actually flowing, our current is flowing in this direction. So in this direction, we see that the far terminal is not this one, but in fact this one. So the far terminal is the negative terminal. So we say minus 3 volts. Lastly, we have V5. So we do a similar trick that we did before, except in this case, since we are in the loop 2, we say I2 minus I1 instead, and we multiply this by R4. So this will be equal to 0, and that is how you sum up these voltages. Next, again, with the same simplification, we replace all the resistors with 3. So we can rewrite this as 3I2 plus 9 volts plus 3I2 minus 3 volts plus, let's distribute the R4 for both I2 and I1. So we have 3I2 minus 3I1, and this is all equal to 0. So let us put the 9 volts together with the minus 3 volts, and let us put the 3I2 with 3I2 with 3I2. Let's just shift this a bit down so we can see that we have 9I2 minus 3I1. This will be 9 minus 3 volts will be 6 volts, but let's take it to the other side so we can get minus 6. So this is our second formula, our second equation that we will use. So this is equation number 2. Now we have these two equations. We're not actually looking for either I1 or I2, we're actually looking for I3. But if we look back up here, we can see that we can find I3 by subtracting I1 from I2. So keeping that in mind, let's find I1 and I2 by simultaneous equations. So let's shift this down a bit. We only need these equations in mind. Let us rewrite these equations. 9I1 minus 3I2 is equal to 3. That's equation number 1. Oh, what is that? Let us get rid of that and say I1. Okay. And we have 9I2 minus 3I1 is equal to minus 6. So whenever you work with simultaneous equations, this is a bit of a math concept, you try to get rid of one of the variables. So let's try to get rid of, let's say I want to get rid of I2, for example. So if I multiply this second equation by 1 over 3, what happens is, let's rewrite it so this can be a bit clearer. The first equation remains the same. Minus I2 is equal to 3. The second equation, I have 9 divided by 3, that's 3I2. I have minus 3I1 divided by 3, that's minus I1. I have minus 6 divided by 3, and that would be minus 2. So what will happen now if we add these two equations together? Well, when we add these two equations together, you get 9I1 minus I1. That will be 8I1, right? And then you have minus 3I2 plus 3I2. So these two will actually cancel out each other. That is the whole reason why I multiplied it by 1 over 3. So you have 8I1 is equal to 3 minus 2, and that will be 1. Finally, we get I1 is equal to 1 over 8. That will be our value for I1. But we also need to find I2. We can use any of these formulas to find I2. Let us try to use this formula right here. Let's use this formula right here to find I2. So we have that 3, let me write this in black. So we have that 3I2 minus I1 is equal to minus 2, correct? But now we know what I1 is, so we can say that 3I2 minus 1 over 8 is equal to minus 2. We can say that 3I2 is equal to minus 2 plus 1 over 8 if we take 1 over 8 to the other side. 3I2 is equal to minus 2 times 8 is minus 16 plus 1. That would be minus 15 over 8. Let's divide both sides by 1 over 3. So we have that I2 will be equal to 15 divided by 3 is 5. So minus 5 over 8, and that will be our value for I2. So we just used some math, simultaneous equations, and solving these equations in order to find I1 and I2. Again, we're not looking for I1 or I2, we're looking for I3. Where do we find R3? Where do we find I3? Well, you use this law right here, KCL, and we see that I3 is equal to I1 minus I2. So let's go back to our values of I1 and I2. So we can come back down here and we can state that I3 is equal to I1 minus I2. I3 will be equal to I1, which is 1 over 8, minus I2, which is minus 5 over 8. So this value, I3, will be equal to 1 minus minus 5. That will be 6 over 8. If I could further simplify that to a decimal, that will be 0.75. So that is our final answer. I3 is equal to 0.75. If we look at our choices, that is choice D, 0.75. Now, I know this seems like a lot. It takes a long time, honestly speaking, and you have to practice it to get the hang of it. But the general things that you have to keep in mind is that there are two laws in order to analyze circuits, electrical circuits. This is KVL and KCL. KVL states that adding the voltages within a loop will equal to 0. KCL states that current entering a certain node is equal to current exiting a certain node. So you have to use both of these in order to answer these questions. You analyze each loop separately, loop 1 and loop 2, and you have a formula that you gain from each. By simultaneous equations, you can find the current in each of the separate loops. In this question, it asked for the current flowing between the two loops. So in this case, you had to use KCL in order to find that current value. In another question, it might have asked you I1, which you could find like so, or it might have asked you I2, which you could have found like so. So it all depends on the question, but it is good to practice the principles of KVL and KCL. And that's it.